Okay. Hello, everyone. Hello, everyone, and welcome back to Stream 3 at DSC MENA 2025. Peace to you all. And we're starting today with Ahmed Ezzat, who will guide us through the fascinating world of diffusion models in generative AI. He's going to take us from theory to coding, and you'll get a hands-on feel for how these models work and what makes them so powerful. Okay, and the floor is all yours, Ahmed.
Okay, thank you, Sarah. Hello, everyone. I hope that all of you are good. Actually, today we will start talking about some interesting topic in generative AI, which is diffusion models. Let me share my screen first to start. Okay. 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 Is the screen is visible now? Can you see my screen? Okay. Okay. Good. My name is Ahmed Ezzat. I'm AI engineer at eConnect Africa. Actually, I'm working mainly on projects that serves in the healthcare and the education majors. Also, I'm working on another projects, but these are my main majors that I am working on. And one of the topics that I'm using in my job actually, and I'm explaining this topic today to share with you the hustle and all of the things that I'm using and I'm working on is the diffusion models. Okay, so we will explore how diffusion models work and how it integrate in Gen AI. And its quality to the output, which make it unique, actually. Starting from the core concepts and to the practical applications, inshallah. Okay. As a motivation to make you listen, maybe with high enthusiasm about this topic, if we looked at this graph or at this image, okay, the impact radar for generative AI, actually this image for 2023, okay, it shows that we have here all of the generative AI topics that differentiate from the mass level and also the range of its existence in the field. Okay, so there are, I guess, a lot of terms that you may be familiar with, and also if we have zoomed a little bit, we will find that diffusion models has a high mass of focus, and also it falls in the very near area, and actually it got in the present, actually the diffusion models, it's used, as we will see, in everything. Okay. And also this is from maybe a practical or from the industry review, okay, but also for the researchers and the academia, this is a graph shows how the rapid of diffusion models research since 2018. Actually, the number of publications has grown exponentially, I guess. So this reflects how these models have become hot topic in both academia and the industry, AI related topics. Okay, and also related to the funny part that most of us recently have waited a lot to or have watched maybe the Ghibli studio style trend, and we all was waiting for it to end. Actually, I don't know if it is or not, but actually people are excited or interested in this topic. So from all of the perspectives, the diffusion model exists. Okay. Regarding the positioning of generative AI, let's start it from the beginning, as the diffusion models of is part of the AI field, but where it is, or let's start from the source of it. Okay, as we know that the artificial intelligence is started earlier in the past century as the to make the machines think and act like a humans, and the Turing test and all of this stuff. Okay, and then the machine learning concept started to make or to train the computers to learn from data without being explicitly programmed. Okay, and feeding the data, or specifically at this time, maybe most of the time it was numerical data, and then the machine learning models like linear regression and these models maybe learn from this data. Okay, and then the deep learning era started by trying to maybe find the patterns in large data sets, and dealing with different modalities, like we have the convolutional neural networks for the computer vision problems, and recurrent neural network for the natural language processing problems, and all of this stuff. Okay, and then actually the generative AI also sets that uh, and it started for creating a new content, like generating a text or images, or maybe, as we see these days, code or anything, maybe also audio. Okay, so this is the positioning of the generative AI as a general concept. Okay, and if we looked at the applications, text generation tasks, we can see it at generative AI, that now everyone using ChatGPT, the students and the professors and the CEOs and the developers themselves, all of us using ChatGPT for text generation. And also there is another application which is video generation. Also, all of us use maybe the existing free tools for video generation, or we have seen it, even results for these videos from different tools like Sura or Runway. Sorry. Okay, and also one of the applications also which we will focus on it today is image generation. Okay, we have seen maybe image fx or Gemini for image creation from Google, and recently this field or this part is very booming, and it maybe a lot of designers and photographers, and also the people who are artists, or the people who are drawing, they are fearing from losing their jobs, as the image generation era started to be very good as a result. Okay, but as we are seeing the final results, or the current results, let's maybe get back and know about the history of Gen AI for image generation specifically, and how it's really started. Okay, if there are any question, I'm talking fast or something. Also, all is good. Actually, I want to just check before continue. Okay, okay. So let's see how the history of Gen AI for image generation. Okay, I guess that maybe even I have just knew this information while I was preparing for the session. Actually, that the first step for the image generation in Gen AI was something called the deep dream. Okay, as shown, Deep Dream is one of the first neural network applications to create art using AI. Okay, actually, it was created by an engineer working at Google, I guess called Alexander. I guess it's mentioned here. Okay, uh, he just thought about running the ImageNet, okay, running the VG16 network, okay, which is consists of convolution neural networks stacked, okay, together. So he thought about running the VGG16 trained on the ImageNet dataset backwards, so he can exaggerate the features that the model learned to classify, so it will impact the image, so that it will results a new image or a new generated image. Okay, it was a very simple idea, but it works. Not a good results as shown here. As for this example, this is the original image. After 10 iterations, this is the results. After 15 after 50 iterations, this is the results. Actually, the results seems like dogs or animals, because the model at this time was trained on ImageNet, and it has many dog and animal photos. So the features that the layers of the model learned exactly, it reflects it on the generated image. Okay, it works, but it's not the best actually, and maybe it hasn't worked for a good usage actually. Okay, but then, as we all know, okay, will appear the most popular topic in generative AI for image generation, which is GANs. Okay, generative adversarial networks. It was invented in 2014 by Ian Goodfellow. Okay, they have created this architecture to resemble or to generate, okay, images, okay, using the also architecture which utilize the deep neural networks, okay, as we will see. The generative adversarial networks components, actually it was consists of two components. Okay, the discriminator network, okay, and the generator network. Okay, and let's check the idea of the GANs. Okay, the discriminator is typically a convolution neural network, as shown here. It's a CNN block, which consists of a convolution neural network, a batch normalization layer, and a ReLU layer. Okay, and its rule, okay, or its job is trying to figure out if the image, okay, which is fed into the network is real or fake. Okay, is it a real image or is a fake image? So its rule in the architecture is like a judge, or like it works technically as a classification model, actually, to be clear. Okay, so this component, okay, which is take the input image, passing it through a classical CNN architecture. Any CNN architecture, you can put it or use it as this component, okay, and then make a decision if the input image is a real or fake image, okay. And the other component is the generator, okay, which is the component that will create the fake images, okay, that the discriminator will be trained on, or will be trained to trying to judge them, okay. So the generator architecture is maybe, as you will see here, is very very similar to the discriminator architecture, but in reverse. Okay, so at the generator, we take a noise vector, okay, totally noise vector, nothing, no features, no any specific extracted feature from any data, okay, it's totally noise vector, and get passed to a reversed convolutional neural network, which we will know later in the following slides, which is called a transpose convolution process, okay, which takes this one-dimensional vector and turn it into feature maps, okay, and then upsample the vector until we can reach it to a full image, and then pass it to the discriminator to check if he will can maybe say it's really a fake image, as it's a generator output. So we will have to train the model again, or we will know that the generator have make an output that fooled the discriminator, so he said that the output of the generator is a real image, okay. And as you can see here, this is the training process. As at the beginning, the discriminator is trying to teach the generator how to generate a good image, okay, like it's a real image. And at the end, the generator succeed, and the discriminator can't maybe differentiate between the generated image and the real image, okay. Okay, and for the inference, actually, we take, also to be clear about the inference, we take the noise and then pass it to the generator, and then it's an output. Nothing is judged. We just take from a total noise vectors to a new images, as the quality of the training data set that we have trained the discriminator to differentiate on, okay. Okay. And the loss function, actually, for the generator is based on how well it fooled the discriminator, and the loss function for the discriminator is based on how well it avoided being fooled, or how well he managed the fake images. Okay, so this is why we call it a generative adversarial network. This is the adversarial process, that each of the components trying to fool each other, okay. And this is why we call it adversarial process, okay. Okay, so this is the war between GAN components, okay. By the end, the discriminator is fooled, actually. Some of the applications of GANs is one of them is style GAN, which is for style transfer. Actually, style GAN was invented by NVIDIA. Okay, it has 3 versions. The rule of this paper, or this architecture, for passing the style from an image to another. Okay, and actually got a very good results. Maybe there some artifacts, but they have maybe made a good output at this time. Okay, so we have style GAN. Also, we have something else called cycle GAN, which is for maybe environment or also style transfer, but it's usually being used for maybe generating images for making a synthetic data sets. Okay, like our goal in generative AI to generate data. Okay, and specifically in GANs we generate image data. So what is our case? Maybe we can have an image. Okay, and we want and this image in the night, and we want to generate the image for the same scene. Okay, in maybe in another time, or maybe in another season. Okay, and maybe it's in the summer and we want to make it in winter. Maybe it's in a sunny scene and we want to make it in a rainy scene. Okay, so we can use model like CycleGAN to generate a big data set, okay, which is called synthetic data. Okay, that we turn our small batch of data, or we have just a small scenes, to a big data set using the generative AI. Okay, and this is one of the main usages of generative AI actually. Okay, to create synthetic data. Okay, so we can use also CycleGAN for such something like this. As shown here, we can see that. Okay, yeah, we have here a real image, okay, for a real scene, and we have an image for Van Gogh style images. Okay, so we have the input image and the generator, which generate the this image in Van Gogh style, and here the generated image is y hat. Okay, and the discriminator here is comparing the generated image, which is here, okay, with the real Van Gogh, and he says that yeah, this is in the Van Gogh style or not. Okay, and the process is reversed actually, that the Van Gogh image is generated in the real style, and that there is another discriminator for comparing the real image, the Van Gogh image in the real image style. Okay, and also comparing if it's real or fake. Okay, so in this architecture, what I want to say here, that in this architecture we have two generators. So this is why it's called cycle GAN. We transfer the style from each image to the another, to the other one. Okay, so this is one of the applications of cycle GAN. Okay, is it clear, or anyone have any question until this part? Any questions? Okay, good. Now let's move to another part, okay, which will also be used as a building block, okay, to explain diffusion model. Don't forget, our topic is diffusion models. We just making our building blocks to reach for this part, okay. Beside the evolution of GAN, okay, there's something at the same time was has appeared at this time, which is a topic called image segmentation. Okay, I guess that maybe most of you know what is image segmentations. Which is we can train a neural network to detect anomalies in maybe X-ray, or maybe an image of this, like for a dog. Okay, and the image segmentation topic actually it's widely used for multiple topics like autonomous vehicles, or maybe for healthcare, or for a lot of topics actually. Okay, and this is an example for it. Actually, you bus for this input image, and the neural network architecture generate a mask, okay, which is separate or segment the object, okay, or the dog here, of the background. Okay, so this is what's called image segmentation. Okay, what if we have combined image segmentation plus GANs, okay, as we have watched in the previous applications. Actually, this is what happened in an application. You can search about it, which is called NVIDIA's Pay. They have combined the two techniques together. So they have trained a model to create images from a segmentation maps. Okay, so this is how maybe most of us, while watching the LinkedIn posts or tutorials about oh, you can draw on a paper, and then you can give it to ChatGPT and he will make an image or something. Actually, actually, I'm not saying it's old, or maybe or we can say it's old, okay, but it wasn't the same quality actually, but it exists. Okay, it's all about the combinations, and maybe the problem is research. Maybe there is another solutions that use more complex architectures more than NVIDIA's Bait, but it exists, and actually I have tried it myself, and it's fascinating, and it has a good output regarding to its time. Okay, NVIDIA's bid at its time, it was a very fantastic idea to combine the two components, the segmentation with GANs. Okay, and I recommend you to try it actually. Okay. Uh, and one of the most popular segmentation architectures, okay, as you know, that we have said that image segmentation utilizes a neural network architectures, or neural network models, okay, and one of the most segmentation architecture, one called UNIT, okay. I guess that anyone know UNIT, I guess, or something. UNet architecture. Okay. Okay. Good. Okay, we will explain it actually. Okay, no worries. But I'm just making sure that some of you know. Actually, you have to search about it, and it's one of the most fascinating architecture at both the academia and the industry. Actually, most of the segmentation models use it as architecture for, or as a base architecture, and maybe making some variations over it. So you have, if you don't know, or if you are interested in the computer vision field, and you are interested about the segmentation problems or something, you have to research UNIT. You will find something good for you. Okay. Okay, let's leverage what are units. Actually, we have talked about GAN. We have said that GANs is about a discriminator network and a generator network, and they are separate components. Okay, the generator takes a noise vector, and the noise vector passed through the network, and it generates an image, and this image is passed to the discriminator to make sure if it's real or fake. Okay, this is for the training process. This is how it's trained, and this is how the components work together. Okay, but they are a separate components. Okay, but now we are talking about unit, okay, which is will be with this very easy trick. Okay, just connecting the end of the discriminator to the beginning of the generator. This is unit actually. Okay, unit, all what it does, okay, that it takes an input image and it down sample it, okay, throughout a convolution neural network, and then it generates a mid, we can say a latent vector, or maybe a vector actually for compressed features. Okay, a feature or the most important feature extracted from the input image, and then it's upsampling it, okay, to a new image, okay, with a segmentation map, and then the two components will be called an encoder and decoder. Okay, the encoder which downsample the image, okay, and the decoder which upsample the vector to a new image, okay, or the result, we can say the result. Okay, okay. So why it's called a U net, okay, as it's shown here, because the U looking, or the U shape which the architecture take. Okay, and regarding the original paper, you have to focus for the dimensions, as the first part, okay, which the input layer, okay, we take the input image in three channels, 128 by 100 by 28 pixels, okay, and pass it to a convolution operation, and then apply another convolution operation, and then apply some convolution operation until we can reach to this latent vector, okay, which is a middle vector, have the most important feature, or the extracted features, okay, and then we will upsample it to this shape, okay, as we have shown in the previous image. This is the dog, and this is the segmented, or the dog with the mask of the segmentation. Okay, and the most important part, that the unit architecture, okay, make sure that at each grade or at each level, okay, it make a copy of this feature map, okay, and pass it to its opposite place, okay, in the decoder line. Okay, so we in this here we are talking about the encoder. Okay, so at maybe at the down zero block, okay, we have here a feature map, an extracted feature from this image. So I will make a copy about them and pass it as a copy and stack it to the features here, okay, which is have a very good impact to make the output of the segmentation problem seems very good. Okay, and this is how unit works. Okay, also, as I mentioned, you can find this unit architecture as we are taking an image, okay, in RGB format, okay, applying convolution operation, downsizing the features, and then until we reach to the middle area, and then we apply a transposed convolution operation which upsample the images again. It's all about matrices multiplication, okay, and it generates the same image with a masked output. Okay, and also you can find this like this tutorials or handouts by Professor Tom on LinkedIn. He has a very good posts about likewise operations like that he is making. Sorry. Okay, he's like making some tutorials or how you can simulate any network like the convolution neural network or maybe UNet network or something like this by numbers. And it's very important to understand and to simulate something like this. Okay, so we have talked about GANs, we have talked about the UNet, okay, and how it's used for the segmentation problem. Okay, now let's start with the diffusion models, okay, which is our main topic, and then we will get it in an easy way. Okay, actually we will start about thinking what is diffusion. Okay, anyone know what is diffusion in English actually, or the meaning of the word diffusion itself? Anyone has any idea about the diffusion word itself? Okay, seems interesting. Yes, yes. Thank you, Muhammad. Spread of something. It's likewise actually. Actually, the diffusion idea, it's like a physics something in physics. Okay, that you have a drop of ink. Okay, completely merges with when you drop it in a clean water glass. Okay, and then you are watching the ink spreading in the water, and you have then the water mixed with this ink. Okay, this is the diffusion. Okay, in diffusion models in AI, we just have the same thing. We are turning a clean image. Okay, we have here a clean water. In diffusion models we have a clean image. Okay, we have a clean image of something. Okay, we are turning it step by step into a noise. Okay, but unlike the ink, we will try to regenerate the image again from this noise. Unfortunately, in the ink example here, we can't get the water clean again. Okay, but actually we will try in diffusion models. Okay, remove the noise. Okay, to produce or reproduce a clean image again. Okay, okay, and one of the applications of the diffusion models, yeah, actually, this type of generative models has raised the bar actually to a new level. Okay, in the area of generative models when it appeared. Okay, and there is a very popular paper which is called diffusion models beats GAN in image sensing. Okay, and this is what we will see now. Okay, okay. One of the type, actually there are before going in details, actually there are many types of diffusion models. Okay, like denoising diffusion probabilistic models as it's shown here. Okay, and there is also noise conditioned score networks. Okay, it's a type of diffusion models. There is also stochastic differential equations. It's a type of diffusion models. Okay, and much more as it yeah, okay, as it's clear. The topic, as I mentioned in the beginning, there is a lot of research in this topic, and there is a lot of architectures of diffusion models. Okay, but today we will talk about the denoising diffusion probabilistic models specifically. Okay, um, And in this, as it's clear in on the right image, okay, instead of actually tracking the movement of the ink, we will now track how we will noise and show, or as maybe if anyone is familiar with computer vision problems, he will know that this image for fashion minist image dataset. Okay, so we will try to add noise over these images and try to denoise it again and return it as a clear image or a pure clean image. Okay. So regarding the denoising diffusion probabilistic models, okay, it consists of two processes. Okay, the first one is the forward diffusion process. Okay, which is gradually the process of adding the noise to the input image. Okay, and the second one is the reverse denoising process, okay, which learns how to denoise the image or removing the noise that were added in the forward process, okay. And from my perspective, okay, and this is my perspective, that diffusion models, as understanding it deeply, is easier than GAN. Okay, as you see, you just noising and denoising. Okay, but GAN architectures, it has a lot of hustle actually. But actually, as I said, it's my perspective. Okay. So as it's clear below, you have this input image making noising, okay, and making the noising process to the noise which is generated, and then you get the clear image. Okay. Okay. But comparing it to GAN, I want to highlight two things before starting to explain each process in detail. Okay. The first thing that which is this is why I'm saying GAN is maybe more complex, but also there's a more highlighted or more important thing to highlight. Okay, that in the forward process, as it's shown, I will explain it in detail, but as it's shown below. Okay, in the forward process, the process is iterative. Okay, I'm trying to iteratively, okay, over multiple steps to noising or adding noise, okay, to the input image. Okay, so the difference here, or that you are in GAN, you are just making it in a one step. Okay, so as we mentioned, as we discussed earlier in GANs, that you are just passing the noise or the noise vector to the generator, okay, and it mapped it to an output image at a one shot. Okay, so this is the first difference. And also regarding the reverse process, okay, it learns how to remove the noise step by step. Okay, and this, as we will know later, what makes the diffusion models a slow model at the generation and at the training process. It's a very very slower than the GAN networks. Okay, as you are working on, or you are processing the forward process iteratively, and you are trying to denoising the noise step by step. Okay. Okay. uh, let's start with the forward diffusion process, which is adding noise step. Okay. uh, Going to, or remembering the ink idea, as we mentioned, we just dropping the ink drop to the clean water, and it goes throughout the water until the water was no longer clear. Okay. Similarly, to generate the noise here, which is in the final step, okay, we are just generating a noise samples. Okay, these noise samples at each step. خلاص. Okay, that for each color channel, as our image has 3 color channels. Okay, so for each color channel, we are generating a random value selected, okay, by or from a normal distribution, okay, or we can say a Gaussian distribution. Okay, so here, okay, we have the clean image. We will go to the next step by adding some value, okay, which is selected from the normal distribution, okay, which its variance and its mean based on the training images, okay, and then this will make the image a little bit noised, okay, as it will be adding more noise at the upcoming steps, and then the image will get by the end of this process will get a full noise, okay, and we call this actually a Markov chain, okay, Markov chain, which is which basically means that the current state of the image, okay, let me zoom a little bit, okay, which means that the current state of the image, we can say that x at t2, okay, timestamp 2, t stands for timestamp, okay, is based on the recent state, okay, and this is called, as I said, a Markov chain, okay, so we are going to call the probability distribution, okay, that we use to generate a noisy image, a Q, okay, and then given the xt, okay, which is, we can say we can start from 0, okay, so the all values or all the possible values in the xt1, which is the next generated image, will follow the normal distribution and based on the recent image, okay, and how, as I mentioned, how much noise we will add at each timestamp is based on something called variance scheduler, okay, and the variance scheduler, okay, is something we decide. Actually, it's not a learnable parameter, it's something we decide, okay. There's an art of selecting it, like I guess that all of you know the learning rate, for example, okay, so it's the same, okay, with the variance scheduler, okay. It's a number we decided, okay, we should add just enough for the model to tell that the change, how much it changed to happen, okay. And if we add too much at once, the model will have a harder steps, as you will add too much noise at the step. So at the denoising process, the model will not have a very clear info about how to denoise all of this, or all the much of the noise that you have asked it to be added, okay. So it's very important to select a good variance schedule value, and it actually it's recommended to start with a small amount of noise. So actually, by the time, as it's clear here, by the time the value of or the much of the noise is reaching to the the maximum level or the full noise level. Okay. Okay. So the final thing, or let's finalize the forward diffusion. Okay, we can maybe okay. I guess we can make it in more clearer example. Uh, okay, let's say that we will start with the image of this dog. Okay, and it's labeled by X. Okay, at time t. Okay, which is t here equals to the 0. Okay, and for simplicity, imagine that this image made of just 3 RGB pixels. Okay, it's only 3 RGB pixels. We can say that maybe this pixel only. Okay, and it's like a vector of, okay, 255 and 0 and 0. Let's make it like this for simplicity. Okay, and so we move to the next step, or the next timestamp, which t equals to 1 here. Okay, then we want to add random, as I said, we from the normal distribution or the Gaussian distribution, we want to add a random Gaussian noise. Okay, for to our image. Okay, which is here. It's these 3 pixels only. Okay, so let's say that we have generated these values to be maybe -2, okay, and 2 and 0. Okay, this is the Gaussian or the noise values. Okay, so the next step is adding these together, okay, which will output a new value for this pixel, 253 and 2 and 0. This is the intensity for this pixel after being diffused or after adding the noise. Okay, and likewise for the whole pixels of the image actually. Okay, so we are repeating again by randomly sampling the values from our Gaussian distribution and using it to randomly adjust the color values of each of our pixels. So we are destroying any order or form or structure that can be found in the image. So it's totally a noise. Okay, and if we repeat this process many times, okay, maybe we can say 1,000 timestamps, or like here 10 timestamps. Okay, what happens that it shapes and it generates a total blurred and completely the dog disappeared and we can't see anything. Okay, like that when your TV have a channel that have a weak signal, it's the same, and fully blurred, you can't see anything. Okay, and also don't forget the variance scheduler, okay, or the noise scheduler. You can it could be called by both terms, okay, which controls how much noise you add. Okay, and also a very, very important note before moving from the forward diffusion process, that the forward diffusion process is infinite process. Actually, there is no end for diffusing the pixels. Okay, you are just trying to destroy the pixel features, so it's infinite. Okay, you will not stop until you determine the number of steps. So here we have a variance scheduler that it's a parameter we will determine, and also the number of steps which we will have to determine, because you are able to diffuse the pixels infinitely, and it will be called still the diffusion process and its work. Okay, so you have to determine how much of timestamps you will make your forward diffusion process. Okay, I hope that with this example it's more clear. Okay, is there any questions or something? Mm. Yeah, score-based generative models is also fantastic, uh, which is like what we have said. Uh, Elastic limit. What are you talking about, or can you elaborate more about what do you mean about elastic limit? Okay, okay. I guess that there is no other questions. Okay, we can move. We can move forward. Okay. Okay, this is as we have explained. Now, let's go for the reverse diffusion. Okay. Um, the reverse diffusion process, okay, as we said, it's we are trying to make the opposite thing. Okay. Uh, so we are trying to reverse the process. Okay. And practically, as we said, we have infinite ways to noise the image, and that this what makes the denoising process complicated, as you don't know, if you don't have an information about what's done or how many steps in the forward diffusion process, it's difficult to calculate, or generally it's difficult to calculate how much of noise I have to remove, or how much or how much of values I have to denoise these pixels. Okay, as the way we have mentioned. Okay, so here this mu theta parameter, okay, it refers to the way, or the average image would be at the timestamp before, as we are reversing the dependency from the forward process. As in the forward process, the x10 image is dependent on the x9 image, but in the reverse process it's reversed. Okay, so we are here are dependent, that the final image is dependent on the or sorry, the x10 x9 image is dependent on the most denoised, or sorry, the most noised image. Okay, as we are trying to denoising the process. Okay, so the trouble here is it's challenging to know what that model exactly, or how to denoise the process. Okay, and also to mention something, that the forward process is fixed in the diffusion models, or the diffusion models type that we have mentioned earlier. Okay, the diffusion process is fixed. Okay, it varies from a diffusion model to another. Okay, in the denoising or the reverse diffusion process. Okay, and this is what here in denoising diffusion probabilistic models that we are explaining, the neural network will attempt to evaluate that how should we denoise our images. Okay, so we may not know the p distribution. Okay, which is here. Okay, but we know, or we are sure that it exists. So we don't know the distribution of this photo, but we know that it exists, that there is an image with this distribution. Okay, so whenever we use the Q distribution of this noise step, okay, as an evidence, or we can use it, okay, as I said, the dependency is reversed, okay, that the image at timestamp t is a sample of the image that is in the timestamp t minus 1. Okay, and what we can do is try to reverse the Q distribution. Okay, instead of making it Q distribution, it will be B distribution. Okay, and we will try to create an estimate for the x at t minus 1. Okay, generating as generating the x as t equal 8 from the at x at the timestamp t equal 9. Okay, and if you want to check the equation and the detailed math, okay, I will actually attach an in detail explanation of this topic, and as a hint, it's based on the Bayes rule actually, and it's very very good or impressive mathematical topic, and you will enjoy it actually. Okay, but if you want to explain or explore it in detail, it will take maybe a lot of time to explain it here in the session, so I will send it as an attachment with the material. Okay, okay, but maybe we can wrap up here, as we said on the other side, that okay, that similar to the process of if I took the breaker with ink and I want to remove the ink, okay, the reverse diffusion is something that I am trying to do like this. Okay, so we start with our image of random noise here. Okay, and then we are going to somehow remove the noise that was added to it in very structured and controlled manner. Okay, so we are trying to reconstruct a clear image and then we are saying that or think of the reverse diffusion as every image of a random noise has a clear picture in it. Okay, this is what I'm saying, what I have said in the earlier presentation, that in each Q probability distribution, we say that the B distribution of it exists. Okay, and this is what happens in the reverse diffusion process actually. Okay, let's move, and this is how it works in details, and as I said, you can check it from the resources in detail. The training, as I said, it's like this. You are fine-tuning, or you are training a diffusion model, or maybe, as mentioned in the meme here, stable diffusion, which is a type of diffusion models. Okay, so you can watch that you are trying to adding noise in a good way actually, and then trying to denoising this noise. Okay, okay. Wrapping up about the part of the or the theoretical part of this topic, that when it comes to working on GAN versus maybe diffusion models, okay, when it comes to this comparison, we will find that GANs is fast, has a fast generation property, okay, which is one-shot generation, and in the diffusion models that it's slow, which is multi-iteration generation, okay. But for GANs, okay, it as it's fast generation model, but it's harder to control it, okay, in one pass, okay. And then controlling something like architectures like cycle GAN or style GAN, actually they have maybe at this time, maybe recently, there are new advancements in this, but it's not actually easy like controlling the generation in the diffusion models, okay. And also regarding the comparison, the adversarial way of training GANs, okay, the minimax objective that the discriminator trying to uh, be a good judge, and the generator is trying to fool the discriminator. So this results that at GAN architectures can have a big problem, which is classes collapsing, okay. That if you are trying to generate images in a different classes, like I want to generate maybe for cats and dogs, or something like this, so the most of the time that the classes is collapsing, and it's hard to maintain the differentiation between, or the variety between the classes, okay, which is not exist in the diffusion process or the diffusion models, as it's not using an adversarial generation way, okay. Okay, just please give me a second. Okay, sorry for the interruption. Okay, uh, I don't know if we have time to, maybe I have some code. Oh, okay, and there's a question. Okay. Um, if I kept going on, is there a step? Would it be reversible to deny the image? As I said, the diffusion process itself, or the adding noise process, actually it's infinite. So you have to limit it. But I think that reaching the irreversible to the noise stage, it doesn't exist actually, I guess. uh, as you just want to limit your parameters. It's all about you. It's not the model actually. You are the one who's setting the variance scheduler for how much noise and the time steps. Okay. So it's not dependent on the architecture more than dependent on how you set the parameters. This is my guess actually for this question. Uh, I think there is a step in noising step will not affect the image. So how we can find this? As I said, I guess that your question about selecting the variance value, variance scheduler value. So it's about art, like the selecting the learning rate. You just get it by experiments and maybe by your experience. Um, I'm thinking, okay. For a segmentation task, should I use single model that handles both the diffusion and segmentation processes, or is it better to use two separate models? Um, Regarding this point, I guess that you will just see how much you want to inject, as you are saying that it's a segmentation task. You have to check first if you really need to use uh, diffusion in your architecture or in your solution. Okay, as I said, the diffusion process, actually, yes, it has its advantages, okay, about the quality and the accuracy and all of this stuff. Actually, I have used recently a segmentation model called, I guess, mevnet or something like this. It was utilizing the diffusion architecture for segmentation tasks, but there is a lot of disadvantage, actually, and it ended up by not using it in production, and I have used another architecture which is more suitable for my situation. As the diffusion models, when it comes to depth or practical practice, you will find that it's a very, very big model. Okay, actually, sometimes it goes to maybe, I guess, 7 GB or something like this. So it's a very big models, and it's very slow to apply a segmentation task if your task is easier than this. Okay, so yeah, first of all, yeah, you have discovered the diffusion models, but don't use it for everything, as as you are really having a problem, so it will solve your problem. Okay, um, but if you will, actually, I guess that you will need a separated components. Actually, it will be an architecture combining two different architectures, but they will be a separately components, or as I said, that in the forward bus it will be something, and in the denoising bus it will be another thing. Okay. Uh, is there any other questions about maybe Gen AI, or or the topic about image generation itself? Okay, actually, I swear that we don't have enough time to run all of the code, but we may share another things. Yeah, actually, ask about anything, and also I will share something. Okay. Mm, okay. Okay, let's switch my share screen. Uh, okay. Sharing. Okay. Uh, uh, uh. Yes. I guess. No, wait. It's not. Is it the full screen? Okay. Yeah, okay. I guess it works. Okay. Regarding the implementation of, I want to share this website if you don't know it. Okay. Regarding the implementation of any architecture, or any paper, mostly any paper you are reading or you are experimenting this paper for the first time. There's a website which is called nn.labml.ai. Okay, you can type it just, and you will reach to this website. it combines a lot of implementations for all of the most popular models that you might face, sometimes an optimizers, specific layers, okay, some techniques like distillation or quantization maybe or something, okay. So here you can find, actually, we have talked today about the denoising diffusion probabilistic models, okay. You will find the same thing that we have talked about, okay, and aligned with its implementation, okay. So it's very, very clear for you to see each step in the mathematical implementation sided with the coding part of it, okay. So as it's shown here, okay, everything is implemented, and actually it's using the most lovable library for all of us, PyTorch. Please always use PyTorch because it's a very good thing to implement your models or your production code with it, okay. So check this implementation. Actually, this is what we was going to discuss in step by step. And also this blog from Hugging Face, the annotated diffusion models, actually I have used part of it for making these materials, okay. It discussing how the diffusion models work, also beside the code, okay. And those two actually those two ways or resources regarding that you want to implement or make your own diffusion model, or you want to implement it from scratch, step by step, okay. But in case you can, in case you want to leverage or explore or use the diffusion models without any further specific implementation, okay, actually you can check here. I guess it's here. Yeah, learn at Hugging Face. Yes, diffusion course. Okay, no, yeah, yes, diffusers library. Okay, you can use this diffusers library. It's a ready to use library, and a very, very a good for you at the beginning. Okay, you can just import the diffusion model you want from Hugging Face, okay, and then use it for any task you want. Actually, in this simple line of codes, you just run this line, you get your image, okay. So as we discussed, the diffusion model is a very interesting topic. Actually, I encourage you to yeah, okay, we can say that it's not popular about learning it or having a learning material about it. Also, if this a question that how to learn about it or how to find a learning material about it, most probably you will find a material about it in books, okay. Rare, very, very rare videos on YouTube, okay. But you can actually take it step by step by utilizing it, and you will actually learn and understand it by practice, okay. And it's very, very, as I said, it's very easier to understand than other generative models, but it's all about having the need to use it, and it will be very fun to use it actually for you, okay. uh, is there any other questions or something in your mind you want to ask about it? All is good. Okay. Thank you, guys. Okay, and thank you for DSC MENA for having me on this online session. I hope that you have enjoyed it, and I hope that you have learned a new thing. Okay. And also, if anyone want to connect with me and ask about anything about the AI or another stuff, you can find actually my LinkedIn account, maybe attached here in my profile in the DSC MENA website. And also, you will find it, I guess, on LinkedIn easily, Ahmed Ezzat. Okay, thank you all.
Thank you, Ahmed. And thank you, Ahmed, for this really enjoyable and enlightening session. I had a good time watching. I hope everyone did as well. Diving now into the next one after a short break.